Okay, am I audible to everyone?
Yes, sir, you are audible.
Okay, so good morning everyone and welcome back to the third day of our 5 days faculty development program ICTEA 2025. I hope you all had wonderful first 2 days filled with new insights, ideas and connections. So let's get started. Today we have with us Dr. Bandyopadhyay who will enlighten us with his knowledge and expertise. Now let's have a very brief introduction to our esteemed speaker. Dr. Bandyopadhyay received his PhD degree in Computer Science and Engineering from the Indian Institute of Technology, Kharagpur in 2017. He worked as a junior project assistant in the VLSI consortium project undertaken by the Advanced VLSI Design Laboratory, IIT Kharagpur from 2008 to 2012. His research interests broadly include formal methods during his PhD. From 16 to 17, he worked as an assistant professor at the BITS Pilani Goa campus. From 17 to 18, he was a postdoctoral fellow at the System Analysis and Modeling Group, Hasso-Plattner Institute, Germany. Next, he joined the NVIDIA R&D team as a senior formal verification engineer from 22 to 23. From 2023 to present, he has been working as a scientist and lead of the software engineering group at the ABP Corporate Research Center, India, Bangalore. There, his primary focus is to apply formal methods in the software engineering domain. He has published several papers in reputed software engineering conferences. He has conducted various workshops as well as filed for 5 patents. Without further delay, I request Dr. Bandyopadhyay to begin today's session. Over to you, Soumyadip.
Yes, thank you, Shidhato, for a nice introduction. So, good morning, all of you, and a warm welcome, all of you. So, let me share my screen. I think, uh, 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 why I cannot share it? Uh, I don't know. The site is unable to see the content in your screen. Uh, I could not able to share it. So, uh, choose. Uh, Shidhato, if I can send my PowerPoint presentation to you, then you can share. I'm unable to share my screen. I don't know why.
No, I can share, but still, you have to check this more option, vertical three dots.
Okay, more option.
No, not more option. It's present now option. Present now option.
Present now option. I click it. If I go to the entire screen,
Then entire screen, yes. Then entire
Sir,
screen.
sir,
then
if it is possible, you can come out of the. I mean, you just you once leave the group and you again join the group again with that meet link. Maybe it will work
okay,
because
fine.
sometimes it happens.
Okay, fine. Let me do once again.
Now it is visible, sir, your presentation.
Yes, thank you. So, just 1 minute. Control L. Okay. Why it is not coming?
Shomodip, please wait for 1 minute. Okay,
Okay.
just
But
wait for
your
1 minute.
screen is clearly visible, sir.
Yes, so I would like to make it the full screen mode. So that's why. Uh,
Click the hide option. Click the hide option.
height.
Top hide option. Meetgoogle.com is sharing your screen, then top sharing, then hide. The lower portion, lower portion. Yes, yes,
That's
hide.
fine. No, but basically, I would like to use this one. That is to full screen this one. So that I'm trying to do it. Uh, okay, just 1 minute. Group it. Okay. Don't know what happened over here. Control L. Yes, fine. Well, may I start now? Hello.
No, it is not visible, sir. If it is not visible.
Sir, your
It
presentation
is not
screen is
visible.
sir, your presentation screen is off, so you can again start the presentation.
Now it is visible.
Yes, 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 sir.
Fine. Thank you.
Perfect.
So sorry for the delay. Um, so good morning, all of you. So today I will talk about little bit new topic and very important topic in both academia as well as the industry, specifically more important in the industrial domain, that is the functional correctness of software migration for industrial automation domain. So um, Shiddat's already gave my introduction, so I'm not going to my detail. So in the today's talk, I partitioned into the two different direction. One is the functional correctness on translation validation. One is essentially is a software migration. Another is purely software migration from the one language to the another language. So these two techniques are very uh, well used in different part of the industry. So now, so first part of the lecture is the equivalence checking of programs for translation validation. Before going to the detailing of my talk, so you can, so you please interrupt me any times, and I'd like to make this presentation in more interactive form, such that the audience can understand this holistic approach in very nice way. So here is the three words that there. One is the equivalence checking, another is program, another is a translation validation. So three words are very important. So first is basically the equivalence checking. The equivalence checking is a technique which is comes under the formal verification. Now, it's general questions. What is the formal verification? So I give you one historical background. During 1971, from France, they launched a satellite, and when it's launched, after the 15 second, it moves in the different directions. And then uh, the plenty of dollars and euros was lost. And then the scientists are thinking why this is happening. What's the reason behind that? Then they find out it's a conversions between some hexadecimal to the from the 16-bit integer to the 32-bit integer mapping. So that translations gives this bug, and that is the software bug. So from then onwards, the formal verification started. Formal verification means it's a mathematical concept through which you can validate whether your systems is working correct or not. That means the correctness of a systems. Whenever you write a program, uh, you already know in your mind that is the what are the specifications of your program. Specification means what are the properties of your program. For example, quick sort, if you write the quick sort algorithm or any sorting type of algorithms, you can find out that is the lefter element is always less than the righter element. So then only you can make then you get a sorted array, right? So so these are the property. Or whenever you design a controller, some control specification, that is on what is the threshold value, on what temperature or what pressure the controller works properly. So these all things are the specification. And under the formal verification, broadly there are the three techniques. One is equivalence checking technique, obviously, where you checks the behavioral equivalence between the original and the translated behavior. I am coming to that in the detail. Another is a model checking techniques, where the specification is a property and the implementation is just like a automata systems or the transition systems, and you checks whether this property satisfies on the transition systems or not. And another is the theorem proving, where your specification is written in the logical form and the implementation is also written in some well form or the logical form, and then you check whether A implies B or not. That means the formal verification is a, in nutshell, it's a one liner, which is basically the implementation implies specification. Uh, is this clear up to this? What is the formal verification? Why the formal verification required, and what are the techniques under the formal verification? Is there any question? Uh, I hope there is no question. So I just move forward. So in the IEEE uh, the top 10 algorithms was depicted, and it says that is it is the great in 20th century. So I hope some of the algorithms you already know. That is, for example, the first Fourier transform FFT, quick sort algorithms. In operation research, you also know the simplex method for the linear programming. E- Even if in the randomized algorithms, you can use the Monte Carlo method and so on. Sorry, any question? Just 1 minute. Any question? Okay. Oh no. Likewise, the photon optimizing compiler is one of the important algorithm under the top 10 algorithm. So you know that the Photon is the first developed compiler, right? And it and John McCarthy and Backer's norm form, the Photon compiler, was written. I'm not telling it's a one of the best important algorithm, but I'd like to tell it's a one of the important algorithms which is under the category of the top 10 algorithm, right? So, note from the David Padua on the photon optimizing compiler. It was written in the CSEM, Communicating SEM 2001. That is why the photon optimizing compiler was the first demonstrated compiler, and that is the possibly automatically generate the efficient machine code from the high level language. So, that is you all aware what is the compiler infrastructure. So it takes the high level code and it it gives the output of the machine level code, right? And to get from the high level to machine level translation, that goes to the different phases. So there is a different phases of the compiler. I hope some of you know that is the what are the phases of the compiler. One is a lexical analyzer, then syntax analyzer, then semantics analyzer, then code optimization, intermediate code generation, code optimization, code generation, and ultimately the machine code. And in every phase, there is a globally symbol table is defined where the symbol tables are referred in each and every phases of a compiler. So the photon optimizing compiler, that is a photon compiler, is a first demonstration f- that is possibly to automatically generated the machine code. Not only the machine code, efficient machine code. Efficient in what sense? In terms of the power, in terms of the scalability, in terms of the power means there are some optimization strategies are there. But suppose you write some algorithm and which takes your code and translate it into the efficient machine code. But there is always a chance that your code might not be correct. Some corner cases will be missing. So one of the techniques is the testing, obviously, but the testing is not always the error prone. So that's why here the formal verification plays an important role over here. So in one liner I can tell to bug is human, but to debug divine. And to achieve this divine, I think the translation validation is one and only options to validate the compiler. So, coming back to little bit history, that is after the end of the Moore's law, you have seen that is the lots of architectures are formed from the PGA to the RISC, and similarly, the the evaluations of the languages are from the ASM to nowadays the Haskell, C, C++, JavaScript, Haskell, Python is also there. But any language will not be pioneer if and only if it cannot be mapped to the architecture level. So who mapped this language to architecture mapping? There is a small, steady but slow processes there, the tortoise, which is like a compiler, which maps from the language to the architecture. In the industry, if you can see that in every day, some architect design a new architecture. When I was in the NVIDIA, I have seen that is the architect in almost in a week they devise an architecture, give it to the verification engineer and tell whether this architecture is applicable to the CUDA programming language or not. But the language developer and the compiler, they are not very fast, because they have to create some passes for each and every construct of the architectures and convert it into the language form. So that is very tedious process. And the architecture knows, if there is no language such that the peoples can write a program, and if the program is not mapped to that architecture will not be used anymore. So that's why, although the architect is a rabbit and they're uh, just biting a carrot, but the and the tortoise is a compiler. Although the rabbit is more faster from your childhood, the fable story, but there is a rope tied between their legs. So that's why, even if the architect move faster, it should follow, that is the progress of a compiler. Without the progress of a compiler, architect never do anything. So that's why they are interdependent to each other. So today, I just take it from the Wikipedia, and the previous slide, the Saurabh Bansal from the IIT Delhi professor, he inspired me to, because I liked his lecture and take the concept from his side. So this is basically, I took it from uh, the Wikipedia. That is to show, that is nowadays, what is the compiler complexity. So 7.3 millions of line of code has been spread across 1 lakh 18,375 commits. So average 16 commits per active day. So this data is comes from the GCC, and 2008 onwards there is a so it's a steadily increasing, but the 2004 to 6 there is a slightly dip over there, just because of the garbage collector. But from the 1990s to till date, it's still increasing. So as the compiler complexity is increasing, so it's very crucial to check whether the compiler is working correct or not. So the problem is that you have a program specs, that means the high level language program, compiler algorithms carefully developed by the expert programmer. Here is an human in loops is there, and which provided solution, that is the optimized machine code. Now here some expert programmer is there, which might make some error. So to bug, as I told earlier, to bug is human, but to debug, divine. So you have to make a method such that this program specs and the optimized machine codes are semantically equivalent. So from this holistic approach, one of the new era of research uh, domain comes from 1999 onwards. That's called the translation validation. What is translation validation? The translation validation is the program often subject to optimize or the parallelize by the compiler. If it is translated wrongly, that gives the software bugs. So it is very essential or very crucial, rather very crucial, to detect whether the source program and the translate programs are equivalent or not. So to do this, we feed these two programs. Suppose it's an equivalence checker. For the time being, you consider this as a magic box which take the two programs, and the equivalence checker gives the yes or no answer. So I map to a decision problem which takes the two codes and checks whether the two codes are computationally equivalent or not. That means in the same input it gives the same outputs or not. If the equivalence checker gives the yes answer, two programs are equivalent. If it gives the no answer, two programs may not be equivalent. So our method is sound but not complete. I'll coming to that, what is the sound and complete. Whenever you prove the correctness, So three things comes into the picture. One is the soundness, one is the completeness, another is the complexity. If you go to the ACM Computing Survey 1990, the George Bacon, he proposed several optimizing transformations which is carried out by the compiler. One is duplicating down, duplicating up, boosting down, and useful move. So if you write any program and in the terminal, if you write GCC space minus fdump space minus 3 space minus CFG space your .c file, you will get some control data flow graph. .cfg file is generated. And every programming language, uh, whenever you write the program, every program is divided into some basic block. So basic block might be the normal basic block where some assignment statements are there. Some conditional basic blocks where some condition is that if it is true, it goes to the one branch. If it is false, it goes to the another branch. And the loop is there. So actually the condition blocks and normal basic blocks, if it goes to the previous number of the lines, then the loop is detected. That means some backage is detected. So here the duplicating down means, suppose in the basic block 0 there is some statement, suppose A is assigned to B plus C, and if we can remove this one and propagate to both BB1 and the BB2, this is the duplicating down. Duplicating up is just like a, suppose here is some statement, you move it to here. So this is basically the duplicating up. Boosting down and the boosting up is more or less the same. So you can boost it through the conditional basic block, and the boosting down is also move up. Sorry, the boosting up is move up from the BB3 to BB0, and the boosting down is from the BB0 to BB3. And useful move, you can move the code in any level. So these are the translation techniques are written in the ACM Computing Survey. So for in our work, we are not going to detail in the translation part. We only focus on the validation part. Suppose you have a two versions. So source program you have written, and after applying this kind of the transformation, you get another program. Now you will check whether the two programs are behaviorally equivalent or not. So there is also some related work is there. So this translation validation method was first proposed by the Amin Nueli in Takas 1998. Then it is enhanced by the Nekula, George Nekula in the PLDI 2000. Further, it is enhanced by the Sudipta Kundu, which was on the high-level synthesis compiler Spark, which was published in the 2008. So this is the one approach. So uh, a- actually, the program equivalence, because we are doing the equivalence checking, is an undecidable problem and not even partially decidable. So that means there is always a limitations, and people can always overcome this limitation. So if you can work in this area, so to getting the problem is not a difficult issue, but to solve the problem is really is a hard challenge. So in the translation validation approach, I break into the three buckets. One is the bisimulation based method, which was first method on the translation validation, and it's a purely the automata based approach, and this can work only on if the structure preserving transformation takes place. If the control structure of your program is changed, this method cannot find out whether the two programs are equivalent or not. Another is the path based method, which is basically the our method. So when we did our research work in IIT Kharagpur, we um, first formulate this method, and now it is enhancing. So first it is proposed by the Karfa et al. Then it is enhanced by the Banerjee et al. I myself and my another friend, and then it is enhanced by the Chomsky et al. And other approach is the inductive inferencing based method, which is more sophisticated techniques till now, I believe, because there is a lots of tools are available. For example, LLREV, Key. So it is first proposed by the Matthias, and it is further enhanced by the Bansal et al., which was published in ASC and the Uppsala. If you can see this all approach, the all are published in the very top-notch venues. But the again, as I told earlier, that is a program equivalence is an undecidable problem. There is always a limitation. So these all methods are working in the sequential program. If we try to validate several parallelizing translation like the PAD4all compiler or the Pluto compiler, we need a parallel model of computation. And what is the parallel model of computation? In our work, we choose the Petrinet model, which captures the parallelism and it captures more vivid way. So our problem definition is that we would like to build an equivalence checker for validating parallelizing translations where the terminations is formally assured. So this is the workflow. This is the source program PS. This is the compiler of the manual translations by the translated program PT. There is a Petrinet model constructor. This is a third-party tool which gives the model MS, which corresponds to the program PS, and model MT, which corresponds to the program PT. And then the program have a loop. How many times loop will be executed, we do not know, because we want to be symbolic data. Symbolic means A, B, C like that, not A equal to 2, B equal to 3 like that. So the concrete value means for the testing, symbolic value means the verification. It goes to the path constructor. I will come to that what path constructor do, but it breaks the model into the set of paths QS and QT. Now we will check for all path in QS there exists a path in QT such that two paths are equivalent or not. If it gives a yes answer, two programs are equivalent. If it gives a no answer, two programs may not be equivalent. So you can find out this tool from here. This prototype of the tool is there, and we use the Simpress tool for Petrinet model constructor. Our tool name is Samatullata, that means the equivalence checking. Let me go to the this one. Is there any question? Any questions? So any question? So before going to technical details, so this is the foundations of the things I'd like to explain you. So if you have any question, please ask me. So in a nutshell, I'm telling that is you have a two program and uh, you have to check whether two programs are functionally equivalent or not. That is basically the idea of today's talk. Fine. Now I come to that how we can do the equivalence checking between two programs. And for the sequential program, there is a lots of methods are there, and broadly there are the three methods. One is the bisimulation, another is path based, another is inductive inferencing. We are going to the path based method, and uh, we also try to find out how if the translation is carried out by the parallelizing compiler, how we can prove the semantics equivalence between two programs. So now I coming to uh, the detail steps. I hope up to this is clear, right? Fine. Anyone can answer me. So, is it clear? So, if you can kindly acknowledge, then I can go to this the next steps.
Yes, you, Shomadip, you can
Fine.
continue. You can continue. And your PPT is not showing. Shomadip, your PPT is not showing. Yes, now it is showing.
So now going back to the example. So if you remember this workflow, this is the source program. This is the translated program. There is a model constructor. This is a third party tool. We are not going to detail. This is the model MS. This is the model MT. There is a path constructor and the path based equivalence checker. So now you can see this is the source program where the X is assigned to 10 occur before the loop and here the after the loop. So now these two programs is going to the model constructor first and which generates this Petri-net model. So here some tokens is there. So P1 and P2 are the mark. So the T1, T2 enable token is removed from the P2 to P4, P1 to P3, and then it's iterates 10 times. And but this token is stuck over here, and then these transitions will be enabled, and token move from um, mm, from P4 to P3 and move to P5. So uh, this is also the Petrinet corresponding to this program. So now these two programs are feed into the path constructor module. And why the path is necessary? Because see here you can see the loop. How many times loop will be executed you do not know. Here it executed the 10 times, but if instead of the 10 if I can write the n, it's completely the unbound. So to do this I we just need to cut the loop into the cut point, and then by the backward corner foci method we'll make a path. So here the cut point introductions rules are: inputs are the cut point, the place containing package is the cut point, and the output is the cut point, and the path from the cut point to cut point without having any intermediary cut points. So here P4, so P1, P2, P4 and the P5 are the cut points. And by the backward corner foci method, this is the alpha 0, this is the alpha 1, this is the alpha 2. So three paths are generated. From this model, figure D, also three paths are generated. Now we have a get the set of paths. If you can remember this figure. So path constructor gives a set of path QS and QT. Now we will check for all path in the QS, that is alpha 0, alpha 1 and alpha 2, there exists a path in the QT, that is the beta 0, beta 1 and the beta 2, such that two paths are equivalent. That means their data transformation and the condition of executions are same. So here you can see that is the alpha 0 is data transformation is 1 and it is equivalent to beta 0. Here also data transformation is 1 and the condition is true. Here is the condition is true. So alpha 0 is equivalent to beta 0. Similarly, alpha 1, that is the VP4 plus 1, here the VP3 plus 1. So if you can substitute it, you get the same result, and here the condition is basically the same. So alpha 1 is equivalent to beta 1 and alpha 2 is equivalent to beta 2. So this checking equivalence expression is carried out by the SMT solver. So to do this, we also need to prove a theorem, that is any computation can be represented as a concatenation of paths. If time permits, I will go to this one, and also this proof sketch, but for the time being, I just go in further with other example, that is example 2. Example 2 is more general. So it this program is compute this function where k is assigned to m star 10 to the power l plus n divided by 10 to the power l if l greater than 0, greater than equal to 0, otherwise it computes m plus n. So this is the source program corresponding this function. And when I feed this source program to Perforall or the prominent parallelizing compiler, it breaks into the two threads and then it is merging. So now you have to prove these two programs are equivalent or not. So this is the PetriNet model corresponding the source program. This is the path and this is the place to variable mapping. This is the PetriNet for the parallelized versions. You can see here is a two threads. One thread is there. This is the another thread. And this is the setup pass. This is the place to variable mapping. And you can see that is alpha 1 is equivalent to beta 2 and so on. Here you can see that is the one path might be equivalent to the more than one path. So using the same method, you can establish the equivalence between these two. But one disadvantage is it's a huge model size. So this work, you can find it out in International Conference of Software Engineering, which is a premier conference, Automated Test and Verification Analysis 2017. And one of the reputed journal is the Acta Informatica. It was published in the 2022. So when I was in the academia, from the 2018 to 22, before going to the NVIDIA, I tried to reduce the model size little bit with the help of my students. So in the previous one, you find that the functions are associated with the transitions. So the post places of a transitions contain the same value. Here we put the set of function associated with the outgoing arc. And on the same program, this is the PetriNet model size. So it is drastically reduced. And the new iteration of the PetriNet model was what published in Asia Pacific Software Engineering Conference 2021. And it also awarded the bronze medal in the ACM student research competition in the grand final. Before it awarded this work is awarded the gold medal in the PLDI student research competition in undergrads category. So me and my undergrad students, Rakshit Mittal, work on this area. But again, there is a limitation. It only occurs for the scalar program. No array handling program in this work we are not handling. So we make it first work. First, we made the tool that is a Samatullata. So if you can see that is the place and transitions over here. But in the next iteration, the Samatullata 2, the model size is drastically reduced here. So in a nutshell, for the sequential program, running time is Samatullata is comparable with the running time of the other sequential MOC-based equivalence checking method. However, Samatullata 2 is more faster than all the other tools. Now I come to that the industrial applications of the equivalence checking method. So when I was in the NVIDIA, I worked on the data path verification group. So if you go to some EDA industry, the scenario of a EDA industry and the semiconductor industry, they are very tightly coupled. So the first questions it might arise, what are the name of the semiconductor industry and what their roles? The semiconductor industry who built the chip, one liner. And can you please tell me which company developed the chip? Anyone? Hello. Can anyone tell me that is which company developed the chip?
Sir, is it Intel?
Yes, Intel. Any other?
I don't know about Nvidia, but might be
Nvidia also build the chip. You know AMD,
AMD. Yes, sir, AMD.
AMD, Qualcomm.
Qualcomm,
Yes.
mainly for
So
mobile processors, I think.
yes. The Qualcomm for the mobile processor, AMD for the processor, Intel for the processor, CPU, Nvidia for the GPU. Nvidia also work on the internal CPU also. NV CPU is there, and various companies are there. For example, a TI, Texas Instrument, is also developed the chip that is the digital signal processing kind of chip. Marvel also developed some chips. ANSYS also developed some chip. ARM, right? ARM processor is very prominent processors are there. So, and do you know what are the EDA companies are? Anyone? Can you please tell me some name of some EDA company?
Sir, can be Siemens, I think.
Siemens, yes, one portion is now it is acquired from the Mentor Graphics, that is a Siemens EDA. Any other company? Any other name of the EDA company? Uh, have you heard the name of the Synopsys or Cadence? So yes, so
Yes, sir,
these
we
are
heard about these things. Also, I think Xilinx.
Xilinx. So yes, so that's it's a good point. That is the
Mhm.
Xilinx is in the 2022. It is taken by the AMD. Okay, so
Okay.
Xilinx is no longer exist. Uh, Previously was there the Mentor Graphics, Magma, then Atlanta, then in Kolkata there is one company was there, that is the Intera Systems. Then it's a Synopsys, Cadence, obviously there, and they are the big shots. Now the Siemens is acquired the Mentor Graphics. So now I'd like to give a very high level overview how the semiconductor industry is intertwined of the EDA. So semiconductor industry build a chip. So they make a design. EDA is a tool vendor for the semiconductor industry. For example, Synopsys provide the tools to all of the semiconductor industry, that is Intel, Nvidia, AMD, etc., Marvel, Qualcomm. They provide the tool that is a formal, both the design verification tool, that is the VCS, and the formal verification tool, that is the VCF. The VC formal, it's called it's a Synopsys proprietary tool. Cadence also provide the tools, that is the Jasper code. So these tools are used to validate their design. There is a big CPU design flow, and using these tools, you can find out whether your design have some bug or not. So before the tape out means before going to the fab, you have to validate whether design is correct or not. So the semiconductor industry just blindly use their tools. How the tools are working, they do not know. And Semiconductor industry give the idea, see, look, these are my design, this kind of the design we would like to verify. Then the EDA is try to abstract out and develop a new algorithms such that they can integrate their algorithms into their tools. So the EDA are the tool vendor for, in a nutshell, EDA companies, all EDA companies, the tool vendor of the semiconductor industry, right? So in the semiconductor industry, there is a two groups are there in the formal verification. One is one group is doing DV, that is the design verification, that is a separate part. It is not under the comes on the every team. So every team, one set of people are doing the FPV, that is the formal property verification. In academia, it is called the model checking. They use the Jasper code and using some clock, they try to debug it in the Verilog code. They try to write the system Verilog assertions. Another is the data path verification, which is the equivalence checking from C to RTL. So in data path verification, how the process is working. So one part is comes from the architectural team, another part comes from the designer team. So architectural team write the design in the C level, C language, and the designer team write the Verilog. Now they compare using the tool the VCF, that is the VC formal tool. Generally, the all semiconductor industry use the verification tool called the VCF. And under this VCF, the DPV is doing by the Hector tool. And Hector gives whether the two versions are equivalent or not. But when I was in the NVIDIA, I make it simple for you. This is a complicated design, but the holistic approach is same. That is, suppose architectural team write a multiplier. So this is the multiplication. You can say sum plus equal to 3j. So here the multiplier is used. And a designer team, to reduce the clock cycle, they write a Verilog code where the adder and shifter is there, which I uh, translated into the C form to make easier understanding. So this is the adder and shifter. Now, if we can feed into the Hector tools, Hector in the unbounded analysis, Hector fails because, as I told earlier, it is a program equivalence in an undecidable problem. So Hector also have some limitations. So Hector fails. Why Hector fails? Because the loop iteration differs over here. So what is basically this one? Suppose the L1 and L2 are two loops. If the two loops iterates the same times in the lock steps, this is the bisimilar. And if the L1 and L2 iterations as differ, then it is the non-bisimilar. That means if one program the loop iterates 3 times, and in another program loop iterates 2 times, and effect of the 3 iterations is equivalent to the effect of 2 iterations. This is called a non-bisimilar program, and Hector cannot find it out. So here we develop it, and obviously it's a significant error, and using this infrastructure we detect the bug. So when the Hector gives the may not be equivalent answer, then our FSMD equivalence checker is triggered, and it takes the C file C to FSMD conversion and RTL to FSMD. Then we checks to FSMD are equivalent or not, and we use here the inductive inferencing based techniques using coupling predicate. We can use this entire framework for the high level synthesis. High level synthesis is one of the important aspects in the hardware domain, that is, which takes the behavioral code and it generates the RTL. So during the synthesis phase, there are uh, several uh, phases are there. One is the basic block formation, another is the scheduling, register allocation, bindings, and controller synthesis. So from the basic block to scheduling, as the control structure is not iterated so much, so we can make it basically that C2C equivalence checker. From the scheduling to controller synthesis, we can do the C2RTL equivalence checker. So as I told earlier that uh, the DPVs comes from the architectural team and the RTL team, the designer team. And if we can prove this RTL to C using some techniques, then RTL to C use the 15 solver and C2C only use the 6 solvers. If we can translate it from the RTL to C and check the C2C Hector patch, then we only use the 5 solver efficiently. And and I just forgot to mention that each and every tool have a huge license cost, and that's totally depends upon the how many solvers are using. If semiconductor industry makes some patch which takes RTL and convert it to the C and then do the hectares, then the license cost is reduced. So using this manner, you can do the C2 RTL. So how you can do it? There is an RTL code, there is a control FSM data path, and then you can write a rewriting algorithm which gives the CDFG model and the CDFG model to C. It's a very reverse engineering process and it's a very straightforward. So suppose, so this rewriting algorithms was written by the Chandan Karfa. It was published. Suppose this is the data path and this is the control path and this is the control signal 10011. So 10011. So when these lines are active, then the micro instructions goes from here. So these are the micro instruction, and these are the data communication takes place over here. So and ultimately to execute this one, it's basically the R1 equal to R2 plus R3. In conclusion of this first part of the lecture, we talked about the path-based equivalence checking in the Petrinet-based models. Then we modified the Petrinet model, an efficient path-based equivalence checker, and we also shows the identify the possible industrial application area for the equivalence checking. You can also use this equivalence checking techniques in the automated evaluation of the computer programming course. For example, let me go to this a little bit detail level, because I hope you are all from the academia. So this work I work with the Karlsruhe Institute of Technology, Germany. It's my personal work. So here, you generally give the for the lab assignment test, you give some program and you run some test cases and checks the students' programs. So using this manner, you are doing right. So now the test cases might be passed even if the hard coding also. So then your evaluation is not fair, right? So if you have any other options, please tell me. So how you can check your the computer programming, that is a C program assignment? Anyone can please tell me? That is, it's a pure test case base or some other approach you did it? Anyone? Hello, hello,
Hello.
hello.
Yes, sir. Yes, sir. Tell me.
So, what kind of the approach you are taking whenever you evaluate the computer programming assignment for the students? It's a manual process or some automatic evaluations you are doing?
Sir, mainly it is manual process only right now.
Okay,
But
that means
sometimes,
that
sometimes it can be automated. But it can be for automated. It can be that objective type question only.
okay. So if I tells you that is give a students to write a program and we will check the program automatic basis. So this infrastructure is not available, right? Okay. So I just tell you the two approach. One is very simple. That is the hacker rank is there where you provide the test cases and the sample solutions and it takes the student submissions and gives that is how many test cases are passed and so on, right? And in each and every test cases you give some weightage how many test cases are passed, accordingly he or she will get the number. Using this manner you make this automated things. For this manner you can write only the one scripts, that's all. Now the things is that some test cases uh, even if the student solution pass, that is the uh, further if we can introspect it very carefully, it might be that uh, they can do the hard coding. So the evaluation is not fair. But we devised an approach where the students give a full program and teachers also write the code, not the test cases. And then we feed into the equivalence checker and equivalence checking will checks whether two programs are equivalent or not. So if it is the equivalence to the master solutions, then it goes to the one cluster. Then the first non-equivalent solutions of the student make the representative solutions, that means the next iteration golden solution, and we checks the remaining the students solutions how many are matched behavioral equivalence with this one, make an one clusters and so on. So you can make a class of things. Now those who are not equivalent you will get the partial marking. For the partial marking what you can do it, you can make some category or run some test cases on it and give the partial marking. Using this manner you can uh, do the automated evaluations. And me and Dr. Matthias Ulbrich, so along with Professor Venkatesh from the IIIT Hyderabad, we are working on it, and soon we hope we will build some tools and also make the tools freely available for any educational institution. So this is the sole responsible, that is the such that the students can get a good feedback and the manual effort of the teachers part will be reduced, and the TA we can make it the zero TA. So only the one or two TA teaching assistants will be sufficient to conduct this one. I hope this will be good for your case because your computer programming course is a huge number of the students can opt this course, right? Because it's a compulsory course for across the team across the streams in the mac out. Another is the model driven engineering. I also doing for the telecom Paris and published one paper on the models. So thank you for the first part. I'm not going to the detail for the validity of the path-based equivalence checking because it's it takes mm, some theoretical detail. If you are interested, you can pinch me, and then we will discuss it. So, any other questions? So here I stop here uh, for the first part. So, any other questions uh, from the first part of the lecture?
Dear participants, if you have any question, you can type in the YouTube live chat box as well as in the Google Meet chat box.
Uh, Sir, this equivalence testing actually in industry, how it is incorporated, as you mentioned just that some designer section, they are designing something. When someone part is developing, they are developing something and finding that equivalence only this thing. I mean, this equivalence testing, its application in industry exactly to bridge these multiple sections of a company or anything else.
No, actually, if you can look by the industrial perspective, every uh, semiconductor industry, the equivalence checking is carried out in every phases. Whenever you design it and whenever the architectural team gives some input, so the equivalence checking is carried out because it's a hand in hand. If in industry this equivalence checking is used to detect, generally the formal verification technique is used to identify the bug. So people are writing the code, but the golden rule is that every 10 lines you have a one bug. This techniques, equivalence checking technique, not equivalent testing. The testing is a concrete value, and the equivalence checking is work on the symbolic value. This is applicable for each and every phases of the design. Otherwise, when the chip will going to the tape out mode, that is the fabrication mode, if there is some bugs is there, it the cost is running out. So that's why before the tape out, they do it very elegantly. So that's why if you can see the size of the team in the formal, so DV person is only the 5 or 4, but the formal verification engineers is a 10, like that in that scale. So always double, because it an exhaustive techniques and it always gives the correct answer. It never gives the false positive results. So that's why the verification engineers is a great demand in every industry, specifically in the hardware and the EDA industry. The formal verification is a huge huge target. So the target in the sense I'm talking about, they have a lack of people, so they try to meet their as per the designer team size. So the peoples are joined in the formal verification team, then due to the exhaustives in nature, so they move to the DV team because there is a comparatively less works out there. So the formal verification team is shrinking, and now due to the age of AI and the era of the AI and ML, people are trying to build something, but they cannot assure that is the whether it's correctly working or not. So that's why in the software engineering domain, I'll come to that because my next part is the software part. What the peoples are doing the LLM, lots of things using the LLM and the GNAI, that is LLM plus DL. They make some things, but it always hallucinates. Sometimes it is hallucinate. So we need to verify this one. So the industry, when they make design a product, so basic principle of the product should be reliable. And when the terminology, that is the reliability, comes into the picture, you need to verify it, and that verification should be in the formally. um, may I answer your point, sir?
Yes, sir. Yes, sir. Yes, sir.
Thank you. So now, may I take a 5 minutes break?
Yeah. Yes, yes, sir.
Okay, just 5 minutes.
Yes, sir. Dear participants, we are having a 5 minutes break. Please join after just 5 minutes.
Yes. Uh, Thank you for giving me the time for the 5 minutes break. Uh, let's go to my second part of the lecture.
Hello. Yes, sir.
Um, my screen is visible.
Yes, sir. Yes, sir. Yes, sir.
Okay. Mm. Okay. So, mm, as I told earlier, that is the equivalence checker is basically two programs and feed into the equivalence checker and it gives the yes or no answer. So, what are the area we are covered in the last half? One is a translation validation. Another is the hardware verification. Another is briefly I give the education technology part where the automated evaluation is carried out by the equivalence checking. So in the today's lecture, in now, I will talk about the software migration verification. So what is software migration? So we developed a tool called the Samatullata for the PLC. So it's a behavioral verification mainly. So for the software migration takes place. So what is the business motivations? Because whenever we work on some industry, there are obviously some business motivations is there. So software migrations, so when the control code m- migrations is needed to have an efficient and up-to-date control systems with the state-of-the-art performance and enhanced security and the regulatory compliance. The code migration must ensure that the new application perform identically with the previous one, minimizing operational risks. It's a very large statement, I understand, but in the in the mm, in the layman language, I can tell that is suppose uh, you have a uh, suppose okay, so this software migrations is uh, widely used in the industrial automation domain. Those industry are working on uh, mm, that industry 4.0 generation. Uh, so there several companies are there. For example, the ABB is one of them. Siemens is one of the companies. Schneider, Rockwell, Backoff. So these are all the industrial automation company. So if you can see their age, they started from the 1800 uh, 25 or someone. So after the first industrial revolution. So during that time, the technology was not very sophisticated. So they wrote uh, control algorithms or the control softwares after the 1960s or the 70s in very primitive language and then their own proprietary language. And when the 1990s, when the ISA 61131 standard is comes into the picture, which is an open source, then the customer told, well, um, uh, I uh, I will build my infrastructures into the newer platform. So first you have to understand what is the cycle of this thing. So uh, the cycle is there is a third party systems and suppose the third party systems might be some chemical plant. Suppose the builder Zuari Chemical Refinery installed a chemical reactors. And when they install the chemical reactor, so no one can go to the inside the chemical reactor and do this chemical process. So that's why we need a remote control systems or some automation is required. So some controller, actuator, sensor, and PID controller are integrated, and all things are written in the software level. And then a customer uh, mm, uh, uh, write a language to running this chemical plant. And this language is very primitive language, and the third party systems are happy it's working. Now when the sophistication comes, suppose the pollution control board comes into the picture and they tell, oh, well, your chemical refinery is the carbon emission is huge, so either you make a necessary actions or we will close your company or the chemical refinery. Then the third party systems auction these things. We try to migrate our platform in our chemical refinery. So from the scratch level, they have to write their own uh, own control module in the newer language. So, uh, but for example, suppose the third party systems software vendor make an auctions where the cements, rockwells, and they told, okay, we will do for your systems for the newer version. Then ABB comes into the picture, and it is comes under the software sustainability. So how you can sustaining your software? That means you have to retain your customer. So for this purpose, ABB told, okay, so don't go for the new systems. We will migrate your old system to the new systems. Additionally, we will make this functionally equivalent. And legacy functional specification is goes to the ABB functional specification, and then the forward engineering control builder machine, and then the things. Now this and this is the heritage system, this is the modern system. So if your model systems are functionally correct, your task is done. And what the benefits is there, it's written the customer, and it's also give the certification that is a yes, the software migration is done. And the testing effort you can reduce from the 30 minutes to the 1 hour. You have to do the testings, and if you can fit into the equivalence checker, it can do 1 to 4 minutes. So the number of the test engineers we can reduce using this manner. Now in the PLC language, that is a programmable logic controller systems, the legacy code in under the ISA 61131 standard, there is a 4 languages are there, 5 languages mainly, but I classify into the 4 recently. The the other green parts is used very usefully. One is a sequence function chart SFC, one is a structured text, which is a programming language, and another is a function block diagram, that is the MBD. So the SFC and sequence function chart language, But the ST is basically the programming language. In this work, we only concentrate on the TCL and the SFC. That means the heritage code is TCL and the modern code is the SFC, and we have to prove whether the TCL and the SFC are functionally equivalent or not. Let's take one example. First, we go to the little bit. So this is the SFC. So here is a ore sensing project. So there is a conveyor belt which moves from the left to right, and there is a L1, that is a load cell sensors is there, which L1 is true. That means the conveyor belt starts. And there is a hyperspectral camera S1 is there, which identify whether the ore is good quality or the bad quality. And if S1 is true, then the C1, that is the pick arm, the crane will pick the ore and going to the iron refinery. And if it is the bad quality ore, it going to the trash bin. So this is the weight, then L1 is true, it is the run, conveyor belt run. Then, sorry, here is the false, and the C1 is true, then it is the pick. Otherwise, it will be reject and it is going on. So the PLC is continuous process. It's a reactive systems. So in the SFC, this is called the steps. This is called the transitions. So and this is called the attribute function. So similarly in the Petrinet, every steps is corresponds to the places, every transitions is correspond to the Petrinet transition, and the functions are associated with the places. Using this manner, using the syntactic sugaring, you can translate the SFC to Petrinet level. Now, one can tell, I can give the two programs to the ChatGPT and will say whether the two programs are equivalent or not. But if you can do it, you can dig your own crematorium by yourself, because the chat gpt don't have any program analyzer, so it always hallucinate. For example, these two programs are equivalent. If you feed into the chat gpt in the st form, you can say that is the two programs are equivalent. Chat gpt says, and it's a false positive result. So it's a very dangerous for the deploying any software. There are the list of tools are available, but 2ls, bricks, cbmc, cpa checker. So I just took it from the sv competition, which is co-located with the takas. Again, it's a well-known conference in the computer science and theoretical computer science and the programming language. So but no, none of the methods is work on the dcs or the plc platform. So our solution is the ps to pm. There is a cafe tool, there is a model constructor MC10, which gives the N0, and the MC2, which gives the N1. Again, there is a path constructor which gives the S0 path in the S1, such that two paths are equivalent. Let's take an introductory example. Suppose there is a conveyor belt, as I told earlier. So this is the SFC corresponding this conveyor belt, and this is the TCL code is written over here. It's a very similar to the Pascal kind of language. There is a model constructor which takes the TCL code and convert it to the Petrinet, and here is a model constructor which converted to the Petrinet, and then we get the two Petrinet model and we checks whether the equivalence is established or not. Let's take a quick demo. Well, so this routine, this is the TCL program, simple TCL program, and the model constructor gives this Petrinet model, and this is the visual representation of the Petrinet model. And this is the SFC Petrinet model. We took it from the the control builder textual representation form. This is the visual representations of the SFC. And this is basically the main equivalence checker code. Here, uh, we checks the two equivalents are two petrinates are equivalent or not, and then it calls the petrinate.p file. So first it read the two files, then it's identify the places, identify the cut points, then the construct the path, find the all paths, find single path, then find the all path, then the extract paths from the identify the cut points, then construct the path cover, then the check equivalence for all path of one model. There exists a path in another model such that two paths are equivalent. And the equivalence checking is carried out by this SMT solver. So we have to hard code it into the SMT solver. Now, if we can fit these two programs, that is TCL and the SFC Petrinate, it takes that is the two programs are equivalent. Another solution is basically we try to reduce the overhead of the model constructor because the TCL is a sequential program. So why we cannot convert TCL to some sequential model of computation, and SFC is very closely related to the Petrinate, so Petrinate to the SFC, and then we checks basically the Petrinate versus the control data flow graph checking. So it's called the heterogeneous equivalence checking method. So for example here, this is the TCL code and this is the corresponding SFC code. So here the executions is written over here, and this is the control data flow graph from the TCL, which is very straightforward. Using the compiler you can get it, and here is the demo how the equivalence checking is working. It's the same for all path. First construct the path, then for all path of the FSMD there exists a path in the pattern such as path level equivalent. So first one is the TCL code. This is the SFC. So here the SFC execution is written. Then this is the TCL Petrinate. This is the takes the TCL file and generate the FSMD and gives the dot file. So first it checks the TCL1.dot file. Dot file means there is a graphism package, and then we convert it into the PNG file to make more visual things, and it's a vector graphics, so that's why you can zoom it in nice way. So you can zoom it now. We can zoom it now. So this is the FSMD model over here for the corresponding TCL code as is shown in the screencast. So then we'll go to the SFC Petrinate, that is uh, here. So this is comes from the control builder output, and we give the one-to-one correspondence over here. And now the SFC dots is also generated using the Petrinate model constructor. Uh, so here we feed the SFC and it generates the Petrinate, and it generates the dot files, and then we convert this dot file to the PNG form using some comment. So yes, So PNG form is created. So now you can see it's more crystal clear. So that's why we make it the PNG form. And then we will go to this uh, first main file, and from where the path-based equivalence checking is there. So first we create a FSMD from file, and then we create an SFC new Petrinet from the SFC, and this is the Petrinet data structure from the SFC, and then this is the FSMD data structure over here. Uh, so the states, transitions, conditions, and the assignment statement. From the FSMD, we also put the cut point, and from the path, from the set of from a cut point to a cut point without having any intermediary cut point, and also the set of paths. From the Petrinet, we also get a identify the cut point, then uh, s- uh, these are the structure, then the uh, single path, then the set of paths. So this is the cut point identification, this is the path between the cut point to cut point, this is a single path, and then the using the union operation we get the set of paths. And in the main file we uh, we just call the m0 and m1 for the path, set of paths, and then we will check for all path in the m0 there exists a path in the m1 such that two paths are equivalent or not. Again we can do the identify the cut points and the paths and so on. Obviously the correspondence also be there, and here the find path between the cut point, and the path based equivalence checker is called over here. It takes two argument m0 and m1, and then the path based equivalence checker routines is called. Here is the path based equivalence checker routine. So it calls, as I told earlier, it calls two path 0, path 1 of model m0 and m1, four argument. If it is true, that means two programs are equivalent or not. And to do this, we need to find out the two entities. One is the data transformation and the condition of execution, and that is carried out by the by method of substitution method. And we make it some string forms and feed into the SMT solver. This is the SMT solver we using. We use the Z3 over here. So this is the canonical form of the SMT solver, and ultimately we feed these two expressions to the SMT solver to check whether the data transformation and the condition of executions are matched or not. Now we will run this code. uh, mm, yes, so the one TCL and another is SFC. So here is only the single path is there, and the two programs are equivalent over here. Now to identify the efficiency, and the two paths are equivalent. Here is the paths of the FSMD, here is the paths of Petrinet model, and two paths are, and the two models are equivalent because here is a single path. Now to make the efficiency of our method, if we can introduce the error in the SFC over here, so these highlighting statements are error, so we manually introduce this error, and then from the SFC, if we can find out that what is the corresponding Petrinet over here, and and then we translated this SFC to the Petrinet, and then feed the FSMD which comes from the TCL code to the Petrinet, so to the equivalence checker, as well as the Petrinet which comes from the SFC is feed into the equivalence checker. And if the equivalence checker gives a no answer, yes, our equivalence checking is correct. So here you can see this is the two SFC error and the TCL, same TCL code. Here the two models are not equivalent because so for this path there is the equivalent path and there is a data transformation and the condition of execution mismatch over here. So we also build a graphical user interface for the user such that one user can easily uh, can deploy these things and easily shows to the customer for the sustainability. So if we can feed these two files, one is the TCL and SFC, two programs are equivalent. Now, if we can introduce, if we can select the erroneous files of the SFC where the manual introduction error takes place, and if we can run the scripts, it takes the two programs are not equivalent, and here some negative paths is written over here. So what is the system architecture over here? So I just give you the give you the people little glimpse of the implementation level. Here is the model constructor. This component takes the TCL and the SFC program as an input and generates the corresponding model in the textual format, model 1 and the model 2. And the model visualization module, so this module, it takes the text file and convert to model dot dot, and then the graphism package we make the model representation. Then the equivalence checking part is the cut point insertions rules. So these are the cut points rules are there. Path construction is the same path construction what we did it in the earlier work, and the path based equivalence checking method compare the paths from the both model. Data transformation and the condition of execution extra, because every computation of a two entity, that is the condition of execution and the data transformation. Similarly, every path of a two entity, because we break the computation into the paths such that any computation can be represented as a concatenation of the path. So we can find out that is basically every path of a two entities are associated. One is the data transformation, another is the condition of execution. Then the SMT solver is integration, because we have to check whether the two paths data transformation and the condition of execution verification customer. So the component interactions. So here is the TCL code, parser, three address code, and one opcode and two operands. So process one model constructor. It gives the TXT format. It gives the format dot representation, and the SFC code also the parser three address code process one, and now it goes to the main component. It is the instance creation of the model. We are doing the process 3, that is equivalence transformation and the condition of SMT solver. We will check for all paths in the M1. There exists a path in the M2 such that two paths are equivalent or not. If it gives the answer, and go on. Other approach we can also illustrate it, because this is the one of the equivalence checking approach. Process 5, process 6 and process 7 is our next approach. One is basically the inductive inferencing based techniques, another is the bisimulation based techniques we can also do it, and also bounded model checking based techniques. So this three approach, if we can combine this three approach and make a complete tools, holistic approach of the tools, and send it to the customer, then the customer will be happy, software is sustainable, and uh, we can return the customer. So this is the big business goals for this one. It has also some theoretical aspects over there, how we can do this one, because some time bisimilarities is also there, because PLC program generally have a time. So every seconds it iterates. As I told earlier, it is a safety critical systems and so on. So the model constructor, then the parser, then it's a AST IR generation, then the basic block identification, then the node of the edges creation, CFG creation, and optional visualization. So this is basically the model constructor part. So this is the phases with the automation studio to the XML and the Petrinet tools over here. Now, as I told earlier and the several times, the program equivalence is an undecidable problem. So it's a very difficult to do that. What are the case if the attribute function is a single statement, we can find out. But if the complex statement is associated with the attribute function, it's we cannot solve it out. So that is the major limitation. Mm, Sorry. Uh, any other questions?
Dear participants, if you have any question, you can ask or you can type in the message boxes.
No, maybe it's wrongly raised. Okay, sir.
Okay. Uh, uh, so this kind of uh, things we cannot handle. So for this purpose, what we have to do it, we have to make some hierarchical modeling. So the one Petrinet is also pointed out some subnet which captures the ST code and so on. Using this manner, we can do the hierarchical equivalence checking. So the component interactions is basically the model generation, visualization, equivalence checking, cut point introduction, path construction, and the equivalence verification. So these are basically what are the language stacks we are using? Python and C Sharp, SMT solver library, TCL parser for the model constructor, and the SFC parser for the model constructor SFC. The potential challenge in the solutions is basically the model complexity. So that is the one of the bottleneck for this formal verification was the model complexity. Handling the complex program leads to the larger model size. Path explosions, finding all paths, and it's very computational expensive, and we have to employ the techniques where the path pruning is efficiently handled. Limitation of the SMT solver is also the limitations of our method, because we check the equivalence between specification, the complexity of the model generation, and the equivalence checking is very depending upon the specific features of the TCL and the SFC. So the class of programs we can support the SFC where the each steps contains a single assignment statement, SFC with branch and loop, SFC with fork and joint construct, TCL with branch and loop construct. We cannot handle the limitations is SFC where the each steps consider the T on we cannot handle, TCL with timing behavior we cannot handle. Another approach of the software migration is basically now I think everybody, even if I just give you the one story of the Microsoft research, the Microsoft research directors is Sriram Rajamani. How many heard his name? Because it's a very fantastic story about the Microsoft Research India. It's not the story of the Microsoft Research Redmond, but uh, uh, in the Microsoft Research India, there is a nice story there. And the director was the Sriram Rajamani. So the Sriram Rajamani, when I met to the Sriram Rajamani in the Popel 2015, he told me even if the programming language scheme, he told that is the why. Then I find out in the DBLP that's in the 2014 in the ICSI, yes, the 2014 ICSI in the Hyderabad, he published one paper on the on the probabilistic programming language. Really fabulous, and the peoples are using the machine learning. Now, the last year FSTTCS conference, I met some Microsoft researchers, Microsoft India researchers, and they told, even in the FM update meeting, formal meter subject meeting, they told that is there is a thumb rule is that you can do any work, but that should be related to the LLM. And the ABB is the customer of the Microsoft. So now the era is basically the LLM, and LLM. I don't know in the next year what will be the LLM. So when I left the NVIDIA, the people are also trying to write the assertions using the LLM. But to blindly support the LLM weeds in the field. So one way we can do it. So the customer have a control narratives. That control narratives is provided by the customer to the vendor. Vendor means the for a simplicity, the customer means suppose the builder Zuari Chemical is the customer and vendor is ABB. So the control narratives is written by Birla Zuari Chemical, and that documentation is given to the ABB. Then the ABB engineers is try to write the control algorithm in their platform. Then it is installed to their uh, mm, plant, chemical plant, or the process industry, or the pulp and paper, etc. So now, suppose the control narrative is an old control narrative, 50 years down the line, the control narrative was written, and now again for the returning the customer, uh, we told okay, we will migrate it, but there is a cold control narrative. So ABB cannot take that is the control narrative 1 second because we have already in some repo is there where the control narrative is there. From the control narrative, some TCL code is there. And then if you can feed to the TCL code and the LLM 131 standard using some nice prompt, and then you can check the equivalence between these two. Then not only you just proof the migration process, but also you can prove the entire ecosystems at all. So this is the overall architecture. So heritage code, LLM to migrated code. There is a model constructor, model 0, model 1, path constructor, path cover, and the path cover 1. Then the equivalence checking. And here also you can do the migrated code, some testing approach can evolve. And using the, you can write the test program, migrated code, and along with the test program, and this test program is comes from the LLM. You can feed it, and then you run to the math IEC, one of the open source transpiler. It generates the C code, and then you run the GCC, use the soft PLC, identify the ticks, and then using the GCOV that is also available in the GCC, you can identify the coverage of the code of the test cases. So using this manner, you can you can do it very easily. Uh, so future enhancement provide the detailed error message and the explanation for the non-equivalence cases. Developed user-friendly graphical interface for the easier introduction and the visualization. Modification of the equivalence checking algorithms for the SFC along with the ST code, and conceptualize the timing behavior as well as the timing and the functional equivalence checking. So thank you. So I just stop over here. If there are any questions, please tell me.
Hello, sir. Just one point from my side. Uh, that the different phases, as you discussed, that the initial few portions actually those are in our curriculum in some part, in some portion.
Hmm.
If we want to train our students that just to introduce these issues, these points, these equivalence and in implication and all these things, then how we will guide them? I mean, what kind of any particular type of training or any kind of something we should instruct them to follow to be familiar with this scenario? And how? Yes, sir.
Yes. So actually, see, for the equivalence checking things, the students need to learn particularly four subjects. One is discrete structure, where the equivalence class is uh, defined very formally. Second is the formal language and the automata theory, where the automata based approach, the equivalence between two automata, equivalence of language. So, what are the complexities over there? What are the undecidable? Why it is undecidable? What are the class of problems you can make it decidable? So, this kind of the things are very essential. Third of all, the programming language, principles of programming language, not only the object oriented things. We have to You have to introduce the lambda calculus and the mu calculus, where the substitutions rules are there, and then they have a flavor, that is the how equivalence checking is working. And fourth of all, the compiler. Basically in the compiler, in generally in the IIT and the bits also, we have seen that maximum time is allocated for the lexicon analyzer to parsing, because the parsing there is a several techniques, top down and the bottom up parsings, and we 80% of the times is devoted on this. So the major part, that is the code optimization, code generation, so there uh, mm, we don't have any time, so because the semester is basically the 4 months, so that's why, so that part, to understanding that part is very important. So if they cover these four topics very clear way, and for the industry perspective, every industry, being a software, being a hardware industry, they use the equivalence checking as well as the model checking. They need a formal verification papers, but in the market the formal verification papers are very less. And also the LLM comes into the picture, so you have to validate whether the LLM output is correct or not, because the LLM is worked on the probabilistic model. It's a neural network, so there is some hallucination is then. Okay, so I think we can wind up. So
Siddhartha Babu,
Okay, yes.
you please conclude.
Yes. Am I audible to everyone?
Yes.
Yes.
Okay. Thank you so much, Dr. Soumyadip Bandyopadhyay, for that insightful and thought-provoking session with lots of industry-specific examples. Your expertise and the way you have broken down the complexities of software migration have certainly provided us with new perspectives and valuable takeaways. I'm sure all of us are now even more equipped to implement these strategies and ideas in our respective domains. Thank you once again for being with us and inspiring us today. So as a gesture of honor, we are presenting a certificate to Dr. Bandyopadhyay, which is displayed on the screen, and we request our esteemed speaker to accept the same.
Okay. Thank you.
Sir, is it visible to you, sir?
Yes. It is visible.
Okay. Thank you.
Thank
Okay.
you. Thank you.
So our next session will be started from 2:30 p.m. sharp. All are requested to join the meeting on time. The YouTube live link will be shared in the WhatsApp group shortly. Thank you so much, Soumyadip Bandyopadhyay.
Okay. Thank you,
Thank you,
Siddhartha.
sir. Thank you,
Thank you.
sir. Thank you.
Thank you.